In this video, we're going to investigate why Ghidra's decompiler sometimes displays variable names as in register name, unf register name, or extra out register name. And we look into how you can fix that. Ghidra's decompiler names these variables like that because the variables are based on registers. And in case of the in or unf variables, these are registers that are read before they have been written to within a function. And in case of the extra out and register name, this is a variable that is based on a register that is used after a call, but that register was supposed to be killed by that call. And we now look at some examples to better understand these types. In order to find these problems within Ghidra, you can use the find potential decompiler problems script. And when you run it, it will pop up this table with the function names and the location and the problematic variable and a description of the problem. And here you can see that within, for example, the function inStack, the problematic variable is the inStack and this hex value. And this basically means that too few stack parameters were defined in the function. And we can now look at that function. And within the function, the problematic local variable is the inStack. And over here, I have the source code of this function that I've written myself. And you can see it has one parameter, 3 local variables, and 2 of the local variables are assigned a value based on the address plus and minus a specific offset of another stack variable. And basically what this does is it takes the address of this variable on the stack and then either adds 100 hex or subtracts 100 hex from that position and then takes the value that is at that position and writes it into the local variable and then returns the sum of these values. And what this does, I've commented down here, it builds the following stack. Before you call this function, the parameter a is pushed onto the stack. You can see it here. Then next, when you have the call instruction, the return address is pushed onto the stack. Then next, the frame pointer is pushed onto the stack. That you can see it here in the function prologue. Basically, the old base pointer is pushed onto the stack. And then after that, space is made for the local variables, which you can see here on the stack. This is the sub ESP right here. And what now this code does is the plus 100 hex accesses the value that's up here in the stack. And this is what's causing the Ghidra decompiler problems. The other case where it accesses the negative value, it doesn't cause any problems because the value is down here. And now the Ghidra decompiler thinks that the value down here is within the stack frame of the function and hence declares it as a local variable, as you can see it here. This is actually this variable here. And you can see here that this has a huge offset of 400 hex plus the offset 10, which are the other local variables up here. But this is basically this value down here, and Ghidra simply declares it as a local variable. However, the other value, it cannot legally declare it as a local variable because it's not within the stack frame. However, the Ghidra decompiler still declares it as a local variable, but with the inStack prefix. And this indicates that this isn't really a local variable of the function, but this is actually some value on the stack. And as you can see here, this actually refers to stack with this offset. And you can see this is a positive offset, and in the case here, it's a negative offset. So Ghidra indicates that this is some value of the stack. The next thing that you can encounter is an in and then a register name. And this could, for example, indicate that a parameter has been passed to a function within a register, or it could also indicate that a function that was declared void actually has a return within a register. Now we're going to look at that function. Again, I have the true source code of the function over here, and what I'm doing in this function, it has two parameters, a and b, but it also has a third parameter in the EAX register, which I then in this inline assembler move into the EAX local variable, and then depending on that EAX value, I either return the A or the B parameter. And you can see here in the Ghidra decompiler, declares this variable as in EAX, and it does so. When you look at the disassembly of this, you actually see that the EAX is first moved into the EDX register, and then from there it is moved into that local variable, and then that is compared against 0. So this is basically very ugly code generated for this up here. And Ghidra doesn't know that this is actually passed as an additional parameter to the function. And to fix that, you can edit the function signature and then add a third parameter, then use the custom storage, and then you can assign this here, the parameter that we just had, to be passed via register, assign it the EAX register, and then Ghidra will automatically assign it the type that is 4 bytes long. It also has the size 4 here, and then you can hit OK, and now Ghidra recognizes EAX as the third parameter, and the code now decompiles to this. Now, the next function that we have is extra out. This means that there is probably something returned from a function within an additional register. Normally on x86, values are returned in EAX, but I've built some code that we're going to look at now here that actually uses the ECX register in addition to the EAX register to return a value. And that function looks as follows. It first calls this return in EAX and ECX. This is actually a function I coded, which you can see here, that returns value both in the EAX and the ECX register, and then returns. Because returning something in the EAX and ECX register is not a known calling convention, Ghidra doesn't recognize this. However, Ghidra here notices that the ECX register used after function, you can see it here. I first set ECX to babe, then I call this function, and then after that I use ECX. The Ghidra decompiler now notices that ECX is actually a scratch register or a callee-saved register. That means that within this function, ECX should have been destroyed or gets potentially destroyed. So Ghidra doesn't know how to handle that code, because in case this call here doesn't touch the ECX, ECX would still be babe. However, by the calling convention, this function is allowed to destroy ECX. And what this function actually does, I previously explained it, it moves 42 and 13, both in hex, to EAX and ECX. However, the decompiler only recognizes the EAX as a return value. Again, we can fix that by editing the function signature, and here we can adjust the storage for the return value, and we need to do custom storage, and then we can add another register, use ECX, and now you see the storage is EAX and ECX. We can hit OK, and now you can see that the Ghidra decompiler now actually adjusts this to a 64-bit number instead of a 32-bit number, and now treats these values as one value. Then last but not least, another example I put together is the missed return value. And if we look at that function, it looks like this. A value is actually returned in EAX EBX, and in this case, the Ghidra decompiler actually misses a return value because, as you can see here, EBX is set to dead, then the function is called, and then EBX is used after the function, and Ghidra logically thinks that EBX hasn't changed because usually a function isn't supposed to change EBX because it's a callee-saved register. But if we now look at this function, what we see is it's again the same as before. We return two hex values in two registers, but because EBX is now actually a callee-saved register, that means we're not supposed to change this. However, the Ghidra decompiler doesn't know this and then assumes that after calling this function, EBX is still intact. Again, to fix this, we edit the function signature, use custom storage, add a second register, EBX, and then hit OK. Then we see it's returned as a 64-bit number. And then we go back. And now EBX is not assumed to be unchanged anymore. And we have this correct return value. Here down here, it's a little bit more ugly than the original source code, which is simply adding three numbers together. Here, they actually use the lower 32-bit of the UVAR, and then this extracts the upper 32-bit of the UVAR1 because it's returned as a 64-bit number. These are the most typical problems that you encounter with the Ghidra decompiler, and most you can fix with adjusting function signatures.